In this video, we'll talk about de Moivre's formulas as an application of our powers of complex numbers. So the main thing we know is we know how to compute the powers of complex numbers. We know if I have z equals r e to the I theta, then the complex number z to the n is just r to the n e to the I n theta. We'd actually get a lot more out of this than just this formula itself. Let's set r to be 1 and see where that gets us. Now I'm just looking at the complex number e to the I theta. Now I know this is the same thing as cosine theta plus I sine theta based on how our numbers are defined. Now what can I do? Well, I can raise both sides to the nth power. And what do I get from that? Well, from that, on the left-hand side, I get e to the I n theta. And on the right-hand side, I get this power of sines and cosines. Cosine theta plus I sine theta to the n. Now, I can rewrite the left-hand side here in terms of sine and cosine again. But this time, I get cosine of n theta plus I sine of n theta equals cosine theta plus I sine theta to the n. And this here is the key point here. I now have a way to write cosine of sine of a multiple of an angle in terms of powers of normal sine and cosine of angles. And that can be super helpful when trying to evaluate complicated angles that you wouldn't know how to evaluate otherwise. That what we had is the idea of de Moivre's formulas. It says that for any theta and for any positive integer n, we have that cosine of n theta plus I sine of n theta is the same thing as cosine theta plus I sine of theta to the n. Or in addition, taking negative n's instead, we have that cosine of n theta minus I sine of n theta, because sine's odd and cosine's even, the negative sign comes out of the sine, equals cosine theta plus I sine of theta to the minus n. And so the important thing this does here is give us a way to compute sort of sines and cosines of higher angles or smaller angles, being able to go back and forth between these two formulas to see how these things all work together. One of the main ways you can use this is to derive double or triple or quadruple angle formulas for sine and cosine. Let's do the double angle here because you've seen these formulas before, but you can also use them to derive triple angle formulas as well in the same sort of manner. So the point is, if we set n equals 2 in the first de Moivre's formula, we get that cosine of 2 theta plus I sine of 2 theta equals cosine theta plus I sine theta all squared. So what I can do is expand out this parentheses here on the right and see what that gives me. So cosine 2 theta plus I sine of 2 theta equals cosine squared theta plus 2I sine theta cosine theta plus I squared sine squared theta. I squared is minus 1. This becomes the same thing as cosine squared theta minus sine squared theta plus 2I sine theta cosine theta. And I know this equals cosine of 2 theta plus I sine of 2 theta. Now, these two are equal as complex numbers. What does that mean? That means the real part equals the real part, and the imaginary part equals the imaginary part. If I extract those two expressions, what do I get? I get that cosine of 2 theta is cosine squared theta minus sine squared theta. And I get that sine of 2 theta equals 2 sine theta cosine theta, both of which you should recognize as the double angle formulas for sine and cosine. You can do the same thing for triple angles or really any power angle you want. You can set this up in the same way. Just expand out the right-hand side. It's going to take more work if it's not just a squared. But you'll get to the exact same answers you want at the end of the day. You'll get formulas to compute cosine of a triple angle or sine of a quadruple angle directly, as opposed to having to go through a step-by-step process to get there. That's the idea of de Moivre's formulas and how they can be used to work on identities for different trig functions and seeing how these things all work together, coming from how you compute powers of complex numbers.